cross-sectional area, A, same area here, and I'm going to say that the pressure at this depth over here, well, it's P2. Well, that's supposed to be the same as this here. And the pressure at this particular depth is P1. And if I consider this chunk of water at rest, this is not water that's moving. I'm considering water, just sitting water at rest. If I consider that, what is the acceleration of that water? Zero. It's at rest and stays at rest. Just sitting water there, no flow of water from here to there. Just imagine chunk of water just sitting there. So the acceleration of that water is zero. And because the acceleration of this water is zero, right? I'm gonna draw the water here that I'm interested in. This is like, I wanna draw a free body diagram of that water. So what are the forces acting on that water? So the water that's above over here is pushing down on this body of water that I'm considering. And it pushes down with a force that I'm gonna call F1, which is acting at the top of this water. And that force is equal to the pressure at that depth, P1, multiplied by the area of that surface of that water that I'm considering, which is A. Agree? And what's the water below doing to this water? It's pushing it up, right? The water above pushes the water below downwards, the water below pushes it up upwards, right? So the force over here, which I'm gonna call it F2, is equal to the pressure there at that depth multiplied by that area. And I'm just, to make the problem simple, I'll make this area equal to that area. And one more force is acting on that water, and that's the weight of the water, right? So you have the weight of the water acting at its center of gravity, and that's the weight of the water, right? And that will be the mass of that water times G, mg, the weight of something, right? So that M is the mass of this water in this region here that I'm considering, right? Now, mass is equal to density multiplied by volume. So it would be the density of the water multiplied by the volume of the water times G. Now notice that the volume of this water that I'm considering there is what? So this volume is just the area of the base times the height, right? So I can write this as the density of the water times the area of the base times the height times G. And since this water that I'm considering a free body diagram of is at rest, and stays at rest, then the sum of the forces acting on that water has to be zero. So if I consider the sum of the y component of the forces acting on that water, which is equal to the mass of that water multiplied by the acceleration, the y component of its acceleration, this is zero, so the sum of the y component of the forces is zero. Suppose I choose up as positive. So I have three forces acting on this water that have a vertical component, right? There's water over here on the right that's pushing to the left, but that's an x component. There's water on the right that's on the left over here that's pushing to the right on that water, but that's also horizontal. So I'm only considering the vertical components. So I have F2 pointing in the positive direction, which is up. I have F1 pointing downwards, right? And that's in the negative direction. If up is positive, down is negative. And I also have the weight of the water, which is the force of gravity exerted by the entire planet on this chunk of water. And that will be minus this, right? I'll just write it like this, mg. And F1 is this, F2 is this. So this would be P2 times A minus P1 times A minus, and then the weight of the water is all of this, right? It's the density of the water times A times H times G. and all of this is equal to 0. And if I bring these terms that are negative over to the other side of the equation, I get P2, notice that the a's cancel, and that equals P1 plus rho G H. Notice that I could say that P2 minus P1 is the change in pressure, right? From here to here. And notice that H, it's the change in, Y2 minus Y1, which is like a delta Y. So I can write this equation, if I bring the P1 over to the other side, as, I'll write it as P2 minus P1 equals rho GH, and then I'm going to replace this by a delta P, rho G, and that will be a delta Y. And if I make this height of this water infinitesimal, then this change in P becomes dP, and then I have the density of the water times G, and then that change in height becomes dy. So this is what you learned in Physics 185, but I just rewrote it in a way that for now looks weird, and then you'll see why I'm writing it like this. And notice that there is a plus sign over here. That means that as the height, or not the height, as the depth increases, the pressure has to decrease. Okay? So this, in fact, I can start with this. I can start with that expression. I can start with dP equals rho G dy, and then I integrate both sides of this equation from P1 to P2. And the integral on the left-hand side is with respect to pressure, so my limits of integrations are values of pressure. Now the integral on the right-hand side is with respect to depth, y. So my limits of integrations have to be from values of y. So I just match the value of the depth over here has to be when the pressure is this, which I call that y1. And the depth over here, y, has to be where the pressure is that, which I call that. But because this is a liquid, and I consider the density of the liquid as uniform, the same throughout, then I can take this outside, and G, well, 9.8 meters per second squared is also a constant, so this becomes dP equals rho G dy, and this becomes P2 minus P1 equals rho G Y2 minus Y1, and this is just P2 if I bring the P1 over to the other side, and then this is just H, right? So I'm just showing you that I could have started with this expression and obtained this. I'm just showing that this, which you learned in Physics 185, is equivalent to this. If I manipulate this a little bit, I get that. Yes? Now you may be wondering, why is he doing this? So the reason why I'm doing this is because in Physics 185, you learn how pressure changes with depth in a liquid which is considered incompressible. What we now want to do, now that we are studying, gases and some thermodynamics, right? What we now want to do is talk about how does the pressure change in the air, which is a gas, which is compressible, where the density of the gas, changes as you go up in altitude. So, in other words, I want to know if I give you a height over here, now this will be y. In fact, I'll call it like that. Now positive upwards, right? What's the pressure over there? Given that on the surface at sea level, for example, the pressure is P naught, like atmospheric pressure. This is like the pressure at zero altitude, or in the atmosphere, or the pressure at zero depth in the ocean, right? It's 1 atm. So what is the pressure up there, for example, at some height y, or what another pressure? What is that pressure at a height or at an altitude y above sea level or above the ground? This may be the ground. If I know what the pressure is at ground level, what is the pressure further up? The thing is that now this air is a gas, and that's compressible. So that means that the density is not constant. Something else that's also true that I'll just give you without showing you where it comes from, but it's a very important piece of information, is that as you go up in altitude, the temperature changes. It gets considerably colder as you go up in altitude. Just going up in altitude. Now forget about the wind or, wind chill factors or anything like that. You go up in altitude and the temperature is just lower. So I want to know, what is the pressure in the atmosphere above sea level or above ground level, given that the density of the air is not constant and that the temperature of the air is not constant? It's a more involved calculation than the one done over here. Over here, you just write this, but then the density for a liquid is, you can think of it as a constant, because it's incompressible. You put it outside, and, to go from here to here, it's a piece of cake. Well, how do we handle this problem where we have not a liquid, but rather a gas, which has a density that's not uniform, right? And on top of that, the temperature changes. If it's not windy and so on, as you go up in altitude in the atmosphere, the temperature drops by 6 degrees Celsius for every kilometer you go up. 6 degrees Celsius. And it does that for the first 11 kilometers. So for the first 11 kilometers, right, let's say this is 0, and then you go here, and that's 11 kilometers above, sea level. In this region over here, it's called the troposphere, the temperature decreases by 6 degrees Celsius for every kilometer you go up in altitude. Now, interestingly enough, from 11 kilometers to about, I think it's about 20 kilometers, the temperature is constant. There's a lot of effects that come into play, and so, but I want to solve the problem. What is the pressure as you go up in altitude up to 11 kilometers? In the what's called the troposphere. Okay, so that's the problem that I want to tackle. And so you still have this expression, except if I just consider a small change in height, I can write it like this. The change in pressure is going to be given by that. Except that what happens to the pressure as you go up in altitude, does it get bigger or does it get smaller? So it gets smaller, so I have to put in a minus sign. I'm going to start with that. That's one equation. The other equation that I need to consider is the fact that the temperature in this region decreases, I said, by 6 degrees Celsius for every kilometer as you go up. So the temperature at some height, suppose the height is y, above, let's say, sea level or ground level. The temperature there is going to be equal to what the temperature is at ground level, but is it going to get colder or hotter, do you think?
Colder.
Colder, so therefore we're going to minus sign. And then we have the 6 degrees per kilometer, so that's called alpha, and then times the height. So in this expression over here, right, this alpha it's 6 degrees Celsius or Kelvin per kilometer. You know, every kilometer that you change, if you go closer to the ground, for every kilometer, the temperature increases by 6 degrees Celsius. But if you go up, away from the ground, the temperature decreases by 6. And then this y over here would have to be in kilometers. So I have to take that into account. So I have to then do, let me write down the formulas over here. I have that the temperature at any height y is the temperature at ground level minus alpha y, where alpha is a constant. It's the 6 degrees per kilometer. I also have that the change in pressure is equal to rho g dy, but now I have to put a minus sign because as you go up in altitude, the pressure decreases. And the other thing that I still need to figure out is what do I do with the density? Because the density is not constant. So what is the density of a gas? Let me consider that over here. If I think, the density is mass over volume, correct? That's the definition of density. So if I consider the air as an ideal gas, as an ideal diatomic gas, then I can write that the pressure times the volume is equal to the number of moles times a constant times the temperature in Kelvin, right? The absolute temperature. I can write the following. The number of moles is the total mass divided by the mass of a mole, right? The total mass of all of us in this room would be the mass of this mole plus the mass of this mole plus the mass of this mole, which is just the mass of one mole times the number of moles, right? So then I have that. So if I plug that in here, I get PV equals M over mole RT. And if I bring this, if I exchange these two, I'm going to get P times the mass of a mole equals the mass over the volume times RT. And this is the density, right? So the pressure multiplied by the mass of a mole is equal to the density times R times T. Which means that the density is the pressure multiplied by the mass of a mole of the gas divided by R divided by T. So I have that expression here. So I have three relationships. 1, 2, 3. And I want to manipulate those to figure out what the pressure is at a specific height above ground level. Yes? Can I erase all of this now?
May I ask a quick question?
Sure, of course.
Why did we put the negative in front of the change in pressure? Is it because as you increase altitude, pressure decreases?
Exactly.
There's less
Exactly.
air.
So y is 0 at, let's say, at sea level or ground level, and then as you go up in altitude, the y gets bigger.
And there's less air above you.
But then there's going to be less pressure.
Okay.
So an increase in other words, a positive dy as you go up will lead to a negative dp because the pressure drops.
Right.
But in the case of the liquid, right, of the water, for example, y, you measure the depth going this way. As you go deeper, 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 as your dy, as you change by dy, the pressure gets bigger. Right? So there's an increase. The delta P is positive. So this is what you have for a liquid. So this is for a liquid with a plus. And this is for a gas with a minus. Yes? So you have to put that physics in. Okay, so now let me do the calculation, taking all of this into account. Can I erase this, everyone? Can I? Good.